Okay, so today I would like to speak to you about supermassive black hole science with the Legacy Survey of Space and Time. This talk will mainly focus on active galactic nuclei, but I will also briefly cover transient supermassive black hole fueling events as well. I have served as the chair or the co-chair of the AGN Science Collaboration for LSST and Rubin since 2006, and this talk is on behalf of the AGN Science Collaboration. And it is a delight now to see Rubin moving toward completion. And if things go well, we hope to see survey operations beginning in 2024. And Rubin should make key contributions to studies of AGN physics, all the various components of AGNs, for example, to understanding AGN demographics and to understanding AGN galaxy connections. And that's especially true when you combine the Rubin data with all of the other powerful, very wide field multi-wavelength surveys that are either in progress or are coming soon. And today I will not be able, of course, to cover all aspects of LSST AGN studies. So my apologies in advance if your favorite topic is not covered. So what I will aim to do is to cover some exciting science highlights. So this is the outline for the talk. I will start off with a brief review of the LSST surveys from an AGN perspective. I'll then talk about AGN selection. I'll then talk about some examples of exciting science investigations, variability studies, transient supermassive black hole fueling, and high redshift investigations. And then I'll end briefly talking about the LSST AGN Science Collaboration. So let's start with a brief review of the LSST surveys from an AGN perspective. And so if you had to summarize the LSST in one sentence, the LSST aims to be a public, optical near-infrared survey of about half the sky in the UGRIZY bands to an R-band magnitude, for example, of about 27.5, based on about 820 visits over a 10-year period. And that type of a survey, which is very challenging, is only possible due to this specialized telescope design, where an 8.4 meter telescope surveys in any individual observation a 10 square degree field with a 3.2 gigapixel camera. And so the Rubin survey aims to be wide, covering, well, essentially the observable southern sky. It aims to be fast. It will be rapidly scanning the sky with 15-second exposures, providing a color movie of objects that change or move. And it aims to be deep. When all the observations on a given patch of sky are co-added, it will be 10 to 100 times deeper than other very wide field surveys. And so this plot here shows an example of an operations simulation of what the Rubin survey may be like. The details are still subject to change. I'll say more about that in a minute. But the main survey is this wide, fast, deep survey with this sort of greenish, yellowish color down here. This main survey has been optimized for homogeneity of depth and number of visits. They aim to cover about 18,000 square degrees of primarily the southern sky. And this main survey will use about 90% of the LSST time, or the Rubin time. And what this survey will ultimately provide is 18,000 square degrees of sky, like this. This is a simulation of the stacked Rubin imaging. And this image simulation only covers 0.03 square degrees. And so Rubin in total with that main survey will generate 600,000 images like this one, in total covering something like 20 billion galaxies and 17 billion stars, all with exquisite photometry, image quality, and astrometry across those many bands. And then in addition to the main wide, vast, deep survey, there's a number of other mini surveys that Rubin plans to execute with the remaining about 10% of its time. Notably among these are these yellow regions here, the so-called deep drilling fields, which Rubin will observe much more intensively and much more deeply than typical patches of sky. And there are presently 5 chosen deep drilling fields. And these are well-studied sky regions: Cosmos, XMM LSS, Chandra Deep Field South, ISS 1, and then most recently the Euclid Deep Field South. Each one of these will be 10 square degrees, except for the Euclid Deep Field South, where they're going to do 20 square degrees at half depth. And these sky regions have been chosen because they have superb and rapidly growing multi-wavelength data, which is critically important for AGN science, of course. And so presently, people are working hard to settle what the exact Rubin cadence will be. And there is a so-called survey strategy optimization process that is ongoing. It's been ongoing since about 2018, in fact, even earlier, when the community submitted a large number of white papers putting forward their ideas of what the survey should be like. But in total, they aim to determine exactly how to observe that main survey and how to spend 10 to 20% of the time on these mini surveys, like the deep drilling fields. And the so-called Survey Cadence Optimization Committee is presently working hard to make these decisions. Some of its phase 1 recommendations are already publicly available, and you can go read those if you're interested. And later this year, or perhaps early next year, they aim to have final recommendations on a baseline survey strategy. And so we're looking forward to seeing how all that sorts out. So now let's talk about AGN selection with LSST and multi-wavelength data. So LSST by itself will be very effective at selecting active galaxies. It will be done with a combination of multicolor selection using all these bands, and that lets you select active galaxies pretty effectively from low redshifts up to redshifts of like 7.5. You'll primarily be doing ultraviolet excess selection below redshifts of about 2.5. And then at higher redshifts, you'll be utilizing the distinctive Lyman alpha forest and its imprinting on the colors to select quasars, for example, at high redshift. And of course, all of this works best at high AGN luminosities, when the AGN is substantially outshining its host galaxy. LSST can also use other techniques. Variability, for example, should be quite powerful because, again, you're going to have in any given band between 55 and 185 samplings over the 10-year period. And this will help you find AGNs at more moderate luminosities, when, for example, the AGN luminosity is comparable to that of the host galaxy. And there already has been some significant preparatory work. Here is some work led by Dimitra DeCicco, who has looked at optical variability selection of X-ray AGNs in the well-known COSMOS field. And she finds that as you go from relatively short timescale analyses, this is a 5-month analysis here, you get some AGNs, these triangles standing out by note of their variability. But then as you go to longer and longer timescales, for example, to this 3-year analysis, you get many more AGNs, your completeness rises substantially, and so on. And she finds that with a random forest classifier right now, she can reach something like 344 AGNs per square degree, which would correspond to 6.2 million over the 18,000 square degrees of Rubin. So you can see very large AGN samples should be coming from variability, for example. And of course, LSST will do even better because it's going to have a longer full 10-year baseline with more epochs of coverage. And the individual epochs will be deeper and probably higher angular resolution, and you'll have more bands to work with. And so variability should be a very powerful way to select these AGNs. And then finally, we'll also be able to utilize astrometry. The AGNs, of course, should not show proper motion, and you can also utilize differential chromatic refraction. And so with the very tight astrometric limits, which will reach down to like 1 milliarcsecond per year at an R-band magnitude of 24th over the full 10-year survey, you'll be able to utilize that to minimize confusion with stars, because many confusing objects, white dwarfs, L and T dwarfs, for example, will often move, and you'll be able to tell that those are not AGNs. You'll be able to discriminate out confusing sources. So those techniques all together make LSST data just by itself very effective at finding AGNs. But then in addition, you'll be able to utilize the Rubin data with all of the contemporaneous and already available multi-wavelength data. And this plot here shows the timescales for various wide field and very wide field surveys. And you can see once you combine, for example, the LSST Rubin data with data from, for example, radio surveys or Euclid and Roman or X-ray surveys, you can get even more AGNs that way. And there'll be a number of techniques you can utilize there. In the radio, you can utilize radio luminosity and radio to infrared flux ratio and radio slope and morphology. And then in the infrared, you can utilize, well, infrared plus optical colors from Euclid and Roman plus Rubin. And then in the X-ray, you'll be able to utilize, the X-ray luminosity and the X-ray to optical flux ratio and the X-ray spectral shape. And all of these things together, combined with the Rubin data, will improve AGN selection even more. And so we've made estimates of how many AGNs we might plausibly expect to discover with Rubin. And LSST will surely detect about 300 plus million AGNs in its 18,000 square degree main survey area. We know that because if you go to very deep sky regions like the Chandra Deep Field South, we know that AGNs get up to about 23,900 per square degree. And we know that the majority of those objects are bright enough that Rubin will detect some flux from them. Now, of course, the question is how many of those can you actually select as AGNs? And of course, obscuration and host galaxy dilution will hinder AGN selection. But we're pretty confident, looking at the Rubin data alone, we're pretty confident you'll be able to get something like 20 million AGNs, so 7% of that 300 million or so. And then we hope, especially utilizing the multi-wavelength data, we hope to get up to 50 plus million AGNs coming from Rubin plus all the multi-wavelength data, which will give us a truly massive sample of AGNs to investigate lots of exciting scientific topics. And so in fact, now let's get on to some of those scientific topics. I'm going to go through now some example AGN science investigations that we hope to do with Rubin. And just thinking about the numbers, they're very impressive. If you just think, every night, Rubin will be monitoring 5+ million AGNs that have been selected as AGNs. Every night, you can hope to detect like 20 large AGN flares from things like blazars. You'll discover like 3 stellar tidal disruption events every night. Every 10 nights, you should get a strong quasar microlensing event. You could hope to discover other exotic things like supermassive black hole inspirals and mergers and so on. So there's lots of exciting things that'll be coming in every night. There'll be more than enough work for everybody in the world to be doing. That's for sure. So I'll just go through a few of these things. So let's talk about AGN variability in general. Well, Rubin's going to provide millions of well-sampled, accurate, multicolor AGN light curves spanning minutes to year timescales with billions of photometric measurements. And you'll, of course, have an even better sampling and depth for the 100,000 or so AGNs in the deep drilling fields. And you can combine the Rubin data with precursor data from these surveys to have even longer time baselines, if that's of scientific value. And then you'll be able to conduct, well, very impressive general luminosity and spectral variability studies of AGNs. You'll be able to characterize AGN variability as a function of luminosity, redshift, wavelength, timescale, color, radial properties, mission line properties, black hole mass, Eddington ratio, and so on. And there are very interesting trends already known in this respect, and you'll be able to quantify these in great detail and pull apart AGN variability in an unprecedented way. And of course, because you have these massive samples of AGNs that you're studying, you'll be able to identify rare but revealing events, strong jet flares, large accretion-disk instabilities, the so-called changing look events, swan song events where AGNs shut off or largely shut off. You can look for quasi-periodic oscillations or quasi-periodic eruptions and so on. You'll have this enormous sample to be probing for these types of rare behaviors. Also, you can very effectively combine the Rubin data with time domain spectroscopic surveys. For example, both Sloan 5 and Foremost are planning to perform reverberation mapping studies of the broadline regions of AGNs in the deep drilling fields over these timescales as listed. And here, of course, they aim to measure black hole masses directly by measuring the reverberation lags of the broadline region compared to the continuum variability. And Rubin will automatically be providing in the deep drilling field, 900 epochs, hopefully at least, of outstanding photometry to aid broadline region reverberation mapping. So you'll have a superbly measured continuum. You can watch how the lines vary in response. You can get time delays and reverberation lags and black hole masses from all of this. You'll also be able to investigate, broad absorption line variability, reddening variability, changing look quasars, in general emission line variability with vastly improve source statistics by combining the LSST data and time domain spectroscopic data. We also hope to look at accretion-disk structure with the LSST data, and I put that word in quotes because some people still debate, the exact nature of the accretion disk in these systems. For example, people have performed accretion-disk continuum reverberation mapping with SWIFT. Here's one example shown here. And they find notably that the wavelength behavior of the lag structure is consistent with expectations for accretion disks. But the surprising thing is the physical size of the structure that's being reverberated appears to be a factor of 2 or 3 times larger than you would expect from standard accretion disk theory, which challenges the basic accretion disk model even perhaps. And so, LSST will be performing in its deep drilling fields, high quality accretion disk reverberation mapping for about 3,000, AGNs. The luminous type 1 quasars are the ones you'll be focusing on here. And so you'll have a vastly improved sample of objects that you can perform these types of continuum reverberation mapping studies to determine what the detailed inner structure of these systems is. You can also utilize a microlens. This will mainly be using the full wide-fast deep survey. There, Rubin will be monitoring about 3,000 AGNs that are lensed into multiple images. And then as individual stars move around in the lensing galaxy and the microlensing caustics sweep along accretion disks, you can hope to obtain effectively nano arcsecond resolution down onto the accretion disk and measure its structure that way. So here you have 2 complementary ways that people can explore accretion disk structure with LSST. And of course, when you have interesting results coming from either of these approaches, these can trigger further multi-wavelength investigations to support what Rubin is doing. And then further on this just sort of general AGN variability stuff, well, you can also look for other remarkable phenomena like small separation binary supermassive black holes. The idea here is that to move from the parsec scale down to the milliparsec scale, well, a binary supermassive black hole system has to lose a great deal of angular momentum. That very likely is done via accretion, and here's a nice simulation of that. And there are predictions that the accretion rate onto both supermassive black holes may vary on timescales of the binary period. And here's a simulated light curve showing some of that variability over a long timescale. And well, those types of timescales predicted for example, a black hole binary with a separation of 10 to the minus 2 parsecs is months to years, which is very well suited to the LSST monitoring. And so LSST will be able to find or usefully constrain the uncertain frequency of these tight supermassive black hole binary systems. And there are already candidates that have been found for these types of objects. Here's one example. Here are some more. And one now needs rigorous statistical sample studies from LSST to investigate these things further. One can also look at transient fueling of dormant supermassive black holes, which are expected to flare to AGN luminosities, and in many cases are observed to do so when a star is tidally disruption and partially accreted. And we, with Rubin, expect to detect 1,000 plus of these stellar tidal disruption events per year. You will have to execute careful cuts to avoid confusion with supernova, for example. But with this enormous sample that will be built up, you'll be able to work out rates of tidal disruptions as a function of galaxy type and redshift. You'll be able to understand the diversity of these events. They have a range of luminosities and apparent effective temperatures and jet powers. Hopefully we'll understand why that diversity exists, and you'll be able to find remarkable events, white dwarf disruptions by intermediate mass black holes, giant planets disruptions, and so on. There'll be lots to do there. And then finally, at high redshift, well, Rubin can utilize the distinctive colors of high redshift quasars, which place them far away from most other sources, to identify these high redshift quasars. That's, of course, due to the Lyman alpha forest and the Lyman break coming in. And there are predictions. Here's predictions from the work by Sophie Reed and collaborators that at redshifts of above 7, you should be able to discover like 55 high redshift quasars from the Rubin data, alone. And then beyond a redshift of 7.5, well, there you have to go further out into the infrared that the Rubin can access. And so you can combine ultimately data from Rubin with data from Euclid and with data from well, Roman, and these missions together will allow quasar discovery at redshifts of 7.5 to 9. Here is a plot showing the depths of the various surveys as a function of wavelength, and these high redshift quasars should be discovered in decent numbers. Here is here are calculations or estimates of what Rubin plus Euclid together should be able to do for AGN selection by Riz Barnett and collaborators, and they predict that it can reach out to redshifts of about 9, although the numbers get pretty small, but redshifts of about 8. But you should be able to get some AGNs reaching redshifts 9. And these will be very exciting to investigate, to look at SED evolution and so on. And then, of course, some of us are also excited to combine Rubin data with X-ray data to investigate high redshift obscured AGNs. And here, well, you can combine, for example, the Chandra and XMM Newton source catalogs, which will have 30 years of archival data available, hopefully, and you can combine that with all of these other surveys and select out high redshift AGNs by their distinctive optical infrared colors and the fact that they're X-ray sources. And this should let you perform an effective redshift 4 to 8 AGN survey. And the important thing is you'll be able to home in on the obscured AGNs, which are often difficult to find in other ways. And we expect to detect, well, pushing 500 to 1,000 sources at redshifts of 4 to 6 and 10 to 100 at redshifts of 6 to 8. And here you'll be able to fill in the obscured AGN population out at high redshifts. And then finally, I'll just say that there are many more science examples that I won't have time to cover today, but you can find more examples in the LSST Science book or at our webpage for the AGN Science Collaboration. In fact, we're having a meeting next week. You can let me know if you have interest in somehow attending that. And then we also have about 15 hours of science talks on YouTube from our 2020 and 21 summer meetings, where many more scientific topics are covered, and those may be of interest to you. Okay, so I'm going to end today then by talking about the AGN Science Collaboration very briefly. The Science Collaboration currently has about 143 members. This is the breakdown by country. We'll say that certainly new members are welcome, but note that the AGN Science Collaboration, membership in the AGN Science Collaboration does not by itself provide you with data rights. There is an in-kind contribution process by which you can earn data rights to the Rubin data. Here are just some plots to show some of the people involved. This is from one of the few in-person meetings we were able to have back in 2017 in Texas. Here are some photos from our 2021 summer meeting, which was held remotely over Zoom. It's very similar to the meeting that we'll be having next week. And here are some more of the folks who were able to attend that meeting. And I will also just say that we have prepared a roadmap document shown here, which defines and prioritizes the activities of the AGN Science Collaboration needed to prepare for Rubin operations. There is work ongoing to address many of the goals in this roadmap, and we are presently working on a revised, updated version of this roadmap, and hopefully that will be available soon. One of the places where the AGN Science Collaboration really has been a leader has been in gathering multi-wavelength data for these deep drilling fields. AGNs being so fundamentally multi-wavelength makes this extremely important. Here, for example, is work led by Mark Lacey and colleagues, where they have obtained very sensitive infrared imaging over 3 of the deep drilling fields, Deep Field South, XMM LSS, and Elias S1. And this shows the location of that survey. It's a very powerful survey in its own right, and of course, it's superbly located to complement Rubin. We also have been leading X-ray surveys of the deep drilling fields. We have recently used XMM Newton via a 5 megasecond multi-year heritage program to get excellent X-ray coverage of XMM LSS, Deep Field South, and Elias S1. We've now detected 10,200 reliable AGNs in the deep drilling fields. These allow immediate exciting science, and also, of course, will serve as a fundamentally important ground truth AGN sample for calibrating LSST AGN selection in the optimal way so that we can take the lessons learned from the deep drilling fields and scale it up to the main survey. And that's how we hope to get to these many millions of AGNs coming from Rubin. It's via calibration of the deep drilling fields. Here are, just briefly, here are the X-ray images from the deep drilling fields. And you can see here, for example, we have beautiful panoramic X-ray imaging all around the Chandra Deep Field South. We also have performed X-ray to far-infrared spectral energy distribution fits recently. We've done 2.8 million of them, in fact, using the Segal code. And here are some examples of SEDs for galaxies and AGNs and bursting and quenching galaxies. Here, we utilize the X-rays to help in setting the level of the AGN component when one is present to disentangle the AGN from the galaxy better than is often possible. And we have been able to perform, well, fairly good measurements of stellar masses and star formation rates for, well, AGNs and non-AGNs. And we hope to use all these data to investigate black hole galaxy connections in the deep drilling fields. We also have been actively participating in setting what the cadence will be, ensuring that the cadence will be good for AGN studies. Here are a number of the cadence notes submitted by the AGN Science Collaboration, and you can have a look at these. They're publicly available at this website, and we're trying to make sure that, you know, whatever the Rubin cadence ultimately ends up being, it will allow many effective and exciting AGN studies. We also are involved in a number of other activities. We're performing data challenge events with monetary prizes to get ready for the Rubin data. People are involved in a data preview program to get their hands dirty with the actual Rubin software and simulations of what the Rubin data will be like. We are, as I mentioned, assessing operation simulations to ensure an excellent cadence for AGN science. We're coordinating with other AGN projects like reverberation mapping experiments. We are advocating for AGN science to broader working groups like the photometric redshift working group for Rubin, trying to ensure that the photometric redshifts for AGNs will be sensible. And we are supporting a contributions evaluation committee, which assesses which international partners are able to earn data rights, a very important thing. We are also we have several members participating in the Rubin Euclid-derived data projects working group, and we perform a number of outreach activities at a variety of levels. So I will wind up there. I will say that we have a website that is available. It has an apply tab. If you have further interest in joining the AGN Science Collaboration, you can check that out. And I will end there. Thank you very much for your time.